Hello, I'm going to introduce my poster titled DDS, a new device-degraded speech dataset for speech enhancement. Device-degraded speech dataset, or DDS for short, is a so-called noisy dataset. This type of dataset contains the noise speech data and its clean speech counterpart that is mainly used for training a neural speech enhancement model. Usually, we can easily obtain or generate such a noise dataset by artificially adding noise and reverberation into a clean speech segment. But recently, the researcher found that the models trained on such a simulated dataset will degrade significantly on real recording condition. There are a few reasons. First, the real recordings are usually degraded by multiple joint factors, including not only noise but also reverberation and bad response of microphone device. Also, the simulated datasets that the simulated long impulse response cannot fully capture nonlinear reverberation component or the nonlinear distortion components for the microphone device. And unfortunately, many of existing datasets consist of only artificially synthetic noise speech. Besides, their size is relatively smaller compared to those used in other domains. So this inspired us to build a large-scale dataset consisting of real recordings. Such real recording condition is very close to the communication scenarios in our daily life, like when we use Zoom at our office or at the home. And we hope such a realistic dataset can facilitate the research in speech enhancement and also for other tasks, such as the ASR adaptation, the TTS on low quality phone data, and even for the replay attack spoof task. Next, about the overall settings of this new dataset. The DDS contains nearly 2,000 hours of speech data collected in 27 realistic conditions, including the 9 environments and 3 microphone devices. It's built on top of 2 existing datasets. The first one is the 4-hour depth dataset, and the second is the 8-hour with decay subset. As this table shows, 9 acoustic environments include the conference room, 2 conference rooms, 2 offices, 3 studios, 1 living room, and 1 waiting room. And we use 3 different microphone devices that has iPad and Uber mic and NPM. In addition, there are 6 different device positions in one recording condition to simulate different noise and reverberation levels. We collect DDS dataset by following the same procedure of the previous steps dataset. We play clean speech recordings using a high-quality monitor speaker and then re-record waveforms in environments. Here's a figure shows a real recording environment. The 3 types of microphones record the played speech at 6 different positions. And after that, we perform cross-correlation algorithm to align the device recorded speech and its original clean speech. Then we conduct an initial analysis of this dataset. We use PASC and ASTY to measure the objective quality and intelligibility of recorded speech respectively. This table shows the results across different environments. We can see each room has a certain level of environmental noise and reverberation, and so this shows the environment variability. We also analyze the effect of device variability, and we can see that the speech recorded by iPad has relatively lower scores. This is because iPad uses a cheap MEMS mic, and the other 2, Uber mic and NPM, use the condenser microphones, which offer better sound quality. These figures shows the quality and intelligibility scores on different recording positions. By recording speech at different positions in terms of distances and angles, we simulate the different noise and reverberation levels. And very naturally, the speech recorded at the closest position, which is A position, has the best quality in terms of quality and intelligibility, while the farthest position, which is F position, has the worst sound quality. A brief summary. In this work, we collect a new dataset, which is DDS. it provides a large numbers of real recordings and features a large variation of speech data, comprehensively covering the common recording factors, including the noise, reverberation, and even microphone device frequency response. But there is still one demerit. The additive noise contained in our dataset is relatively moderate. So if users want the data with more challenging noise levels or more diverse noise types, they might need to artificially add more noise into our dataset. And next, we tested 3 baseline systems on our new dataset. Specifically, we selected 3 baselines. They are the DCCN, which is Deep Complex Convolutional Recurrent Network, which performs very well in the first deep noise separation challenge. The second one is denoising WaveNet, which is an end-to-end waveform prediction model based on the original WaveNet architecture. The third one is Meyer mapping systems. It is a 2-stage pipeline. In the first stage, we predict the clean Meyer spectrogram using an enhancement model. And in the second stage, we generate clean waveforms using wave-hour code instead of using the traditional inverse STFT. We prepared 5 training sets to comprehensively investigate the effect of recording diversity on the model performance. The test set consists of 500 utterances recorded in living room condition by using UberMac. There are 5 training subsets. The D1 set has 32 hours speech data recorded in living room by using UberMac. So you can see the D1 shares exactly the same recording condition in terms of environment and device as that of test set. So it is regarded as the closed set. The D2 also has 32 hours speech from one unseen room by using one unseen device. So it is regarded as open set. The D3 also 32 hours speech recorded in one unseen room by 2 unseen devices. D4, the speech data recorded in 4 unseen rooms by 2 unseen devices. The D5 is from 8 unseen rooms and 2 unseen devices. So in summary, each subset has the same dataset size, the dataset duration, which is 32 hours. The D1 is on matched condition, and D2 to D5 are on mismatched condition. Also, from D2 to D5, they are intentionally designed with increasing recording diversity in terms of recording environment and recording device. Results are given in these figures. So the first, we can find the mismatch between the training and test set affects performance. The model performance on open sets, like in D2, is much worse than that on closed sets, which is in D1. The second, the performance can be clearly improved when we increase the recording diversity. From D2 to D5, we can see both the quality and intelligibility scores increase. And when the recording diversity is good enough, the speech enhancement performance on the open set D5 can even better than that on closed set D1. So this means enhancing the recording diversity of the training set is quite crucial for improving the model's generalization capability. Last, for conclusion, in this work, we introduced a large-scale device-degraded speech dataset. It contains the studio quality clean speech and its aligned low-quality versions with nearly 2,000 hours of real recordings collected under 27 conditions, spanning 3 devices and 9 realistic rooms. We reported several baseline results on DDS and showed that the beneficial effect of recording diversity of training data on the model performance. The dataset is public, which can be accessible from this QR code. And that's all. Thanks for listening.